In the previous session, we looked at various types of homomorphisms, and one of them was isomorphism. So let's look at it in more detail. Given groups G under star operation and group G prime under star prime operation, let F be a homomorphism which maps G to G prime. So F of A in G is equal to A prime in G prime. So F is an isomorphism if F is bijective, that is one-to-one and onto. So if E is in G, E prime is in G prime, and F of E is equal to E prime, then we can say F of A inverse times FA is equal to F of A inverse times A is equal to F of E, which is equal to E prime. So here, how did this F of E came? Because A inverse times A is E. And this implies that F of A inverse is equal to F of A inverse. Now, since F is isomorphism, its inverse, that is F inverse, is also an isomorphism. Remember, F is one-to-one and onto. So in the reverse direction also, it will be the same. So F of A to the power of n is equal to F of A is A prime. So A prime to the power of n, which is equal to F of A to the power of n, which is equal to F of E, because n is the order of G. So F of A to the power of n, A to the power of n is E. So F of E is equal to E prime, which implies that the order of F of A divides n. Now, since F is bijective, that is one-to-one and onto, no smaller power can give E prime. Hence, order of F of A is equal to n. So first we showed that it divides n, and then we showed that it is actually equal to n. Now, F is isomorphism. Its inverse function, F inverse, which maps G prime to G, exists and is also a isomorphism. So F inverse of E prime, what is this going to be? Reverse mapping. It will map to E. It will be equal to E. So F inverse maps E prime to E. Similarly, the inverses are also reverse mapped, or in the sense it is preserved. So that means order of F is equal to the order of F inverse, since both F and F inverse both are one-to-one and onto, which implies that order of G is equal to order of G prime. Okay. Now, isomorphism is an equivalence relation. Now, to show that it is an equivalence relation, we have to show what? That it is reflexive, it is symmetric, and it is transitive. So, reflexive means what? To itself. So, G is isomorphic to G implies that F maps G to G, where F of X equal to X. It is also symmetric. If F maps G to G prime is an isomorphism, then F inverse maps G prime to G is also isomorphism. So that means that F is symmetric. Now, transitive, if G is isomorphic to G prime, which is in turn isomorphic to G double prime, and M maps G to G prime and N maps G prime to G double prime, then the composition of M and N, that is N composed with M, maps G to G double prime. So since it is reflexive, symmetric, and transitive, we can say isomorphism is an equivalence relation. Now, cyclic groups of same order are isomorphic. So let's take example. G let it be the set of integers under addition modulo 3, or more specifically, the set of congruence class integer modulo 3 under addition modulo 3 is G. And let's say the set of cube roots of unity under multiplication is G prime. Now here the homomorphism F, actually this becomes a isomorphism. So F maps G to G prime, where f of k is equal to omega to the power of k, where k is in G. So let's very quickly do this. So f of 0 in this group, f of 0 will take you where? It will take you to omega to the power of 0, which is 1. So 0 to 1. Similarly, if we take f of 1, we get omega to the power of 1. If we take f of 2, we go to omega square. Yes. Similarly, we can take the products, or in this case, the sum of any two elements will map to a product of the corresponding elements here. So F maps G to G prime, and F inverse maps G prime to G. So we can say that G is isomorphic to G prime, or straightforward we can say that Z3 is isomorphic to the group of cube roots of unity under multiplication. Now let's look at some interesting points. Any cyclic group of order n is isomorphic to the additive group of residue classes modulo n. Any group of prime order P is cyclic and therefore isomorphic to ZP. Any infinite cyclic group generated by G is isomorphic to the additive group of integers through a homomorphism n maps to G to the power of n. Any subgroup of the infinite cyclic group is isomorphic to the additive group of integral multiples of an integer. So here the difference between these 2 points is, here for we are talking of a cyclic group generated by an element, whereas here we are talking of a subgroup of the infinite cyclic group. For an isomorphism to exist between two groups, their orders have to be the same, because isomorphism is bijective, that is 1 to 1 and onto. And isomorphism partitions all groups into equivalence classes, where each class contains all groups that are structurally identical. These are called isomorphism classes. Basically, what this means is that we saw with respect to two groups isomorphism. So like this, there can be a lot of different groups which are isomorphic to the any one of these two groups. So that all those groups would form a isomorphism class. And like this, there can be different isomorphism classes. So that was isomorphism. Again, let me remind you, there is a link to a PDF book which describes all these in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now. Bye.